So let's look at how to find the domain of rational functions algebraically, and then we'll also take a look at the graphs and see how this is working out. So again, our rational functions, so rational function r of x comes from a numerator and denominator that are both polynomials. So they could both be some function of x, and our restriction on the domains coming from the denominator. Really, we're just focusing on the denominator, and all of this is based on that whatever that denominator is, it cannot equal 0. So that's what we want to look for. In terms of our domain, x can be absolutely anything except for the thing that would make our denominator 0. So how we'll go about this is for our first function. So we just want to focus on the denominator, and we're saying that x minus 5 cannot equal 0. And then we can solve it just as we would an equation. It's just that we're saying does not equal. So I'd add 5 to both sides. So we're saying x cannot be equal to 5. So for our domain, I want to express it so that x is defined absolutely everywhere except for 5. So we can have everything from negative infinity up to 5 but not including 5, and then starting at 5 but not including 5, off to positive infinity. So let's look at the graph. So we're looking at this 2x over x minus 5. So we can see it has that rational function shape of that 1 over x, and there's a one spot that it's not defined, and that's at x equals positive 5. So that's where our vertical asymptote's coming in, is at that vertical line at 5. So there's that function. For our next function, we're focusing on just the denominator. The numerator has restrictions for for the range. We're just focusing on the domain here. Range gets really tricky, and really we just need the graph for range, but for domain we can find it algebraically. So take the denominator, so t squared plus 10t minus 24, and we're saying that cannot equal 0. So I'm going to factor. So factoring, so two values that multiply to negative 24 and add up to 10, that's going to be my 12 and 2. So I'll need a positive 12 and a negative 2, and that factored form cannot equal 0. And then I can split it up into t plus 12, that cannot equal 0, and t minus 2 cannot equal 0. So subtracting 12 from both sides, t cannot be a negative 12, t cannot be a positive 2. So for my domain, I'm not allowed to have either of those values for x. So what I want is starting at negative infinity, I can have absolutely everything until I get to negative 12. And then I could have everything from negative 12 to positive 2, just not including those endpoints, and then to infinity. So I'm going to have kind of these three intervals. Negative infinity up to negative 12, but skip over negative 12, but go to 2, but skip over 2, and then head off to positive infinity. So the graph for this one will look like this. So what's a little tricky with this one, so we can see our negative 12 here, so you can see a vertical asymptote. But our other one at positive 2 isn't as clear. It's not coming through as a vertical asymptote. It's called a hole in the graph. If I can just get my mouse to hover over it, if you can see it's kind of switching. There it is, 2, undefined. Everything is graphed around it, but at exactly x equals 2, that point's undefined. So it's hard to see. In fact, it's pretty much impossible to see in this form of the graph. But by solving algebraically, we were able to find this hole in the graph in this spot where our function's actually undefined, even though visually it's not coming through that way, but there is this undefined spot right there. So if I was graphing this on a piece of paper, I would be drawing an open circle at that point there to show that we have our function and it's being graphed, but then right there we skip over and then go off to positive infinity. All right, our next piece here is that x squared plus 10 cannot equal 0. I'm going to subtract 10 from both sides, then I can take the square root of both sides. So square root, got too close there, square root, and we're taking a square root of a negative number, and that can't happen. So what that means is, and this is where the wording will get tricky, but we're trying to find restrictions on x here, and this basically shows there are no restrictions for x, which means for our domain, we're going to have all real numbers. X can be absolutely anything. So all real numbers, negative infinity to positive infinity. So if we look at the graph for this one, you can see this function that's defined absolutely everywhere. So that one's all good, all real numbers. Okay, with this last one, we're saying t squared plus 3t cannot equal 0. I can factor out t from the left-hand side, so we end up with t times t plus 3 cannot equal 0. So we're seeing t cannot equal 0, t plus 3 cannot equal 0, which means t cannot equal negative 3. So I can have everything from negative infinity up to negative 3, but I want to skip over negative 3. And I can have everything up to 0, but I want to skip over 0, and then we can go off to positive infinity. So we're going to go from negative infinity up to negative 3, and then from negative 3 up to 0, and then from 0 off to infinity. So at the graph for this one, we can see here, we can see two vertical asymptotes. One's occurring at negative 3 here, so our function's defined from everything from negative infinity up to negative 3, where our function's not defined. But then just to the right of negative 3, we can see our function's defined up until 0, where we have a vertical asymptote, and then we can see our graph off to positive infinity.